Swayam Prabha. Digital India. Educated India.
Okay. So, today we begin with again the lithiation for the 5-member heterocycles, but before that we will just take up the problem I gave you in the last class. It was a problem on lithiation on the saturated heterocycles, and that too is a pure nucleus. If you recall, the problem was on thebaine. Thebaine is a morphine derivative. So, morphine derivative is described as a phenanthrene kind of molecule and furophenanthrene type of molecule. So, I write the phenanthrene structure and then you have a furan nucleus. Occasionally morphine also is classified as isoquinoline derivative. Actually, the biosynthetically it is derived from benzyl isoquinoline. And this the thebaine has a structure where you have a methoxy group, one of the benzene ring is aromatic, and then subsequently all we had a structure of this kind where we have a methoxy. And the first reagent was butyl lithium, and then timeda. Timeda is an additive which is often used to make the base as more basic. And then it was treated with TMS chloride. So, TMS chloride, and then obviously there is a selection in the site of this lithiation. Instead of ortholithiation, what happened? The reaction took place. The reaction took place at the sort of you can say alpha position, alpha to the oxygen, that means the lithiation took place here, and then rest of the things as it is. Then you have this N methyl group up here. So, N and this. So, if you then if you use the TMS chloride, what you will find? You will find again the nucleus remains as it is, then you have this nitrogen, all these things, then this is a bridge here, and then you have OMe, and you get this silicon incorporated in the position alpha to the oxygen. That is perfectly all right. That means only thing that you have to note that the ortholithiation is not the dominant one, it is a CH activation, you can say CH lithiation, sp3 CH lithiation is primarily, and then rest of the things as it is. What next? Then it was L selectride. I think I will not write the structure. What is it? It is a boron kind of, it is a boron hydride. It is basically boron hydride, and you have several groups, and then the counter ion is lithium. And it is named so because of their reactivity pattern. When you say, I mean the name implies it is somewhat selective, then you have to also know what is the selectivity about. Selective, actually the name actually originates from the selectivity of this reagent towards reductions of the cyclic ketone. If you reduce a cyclic ketone, you are like if it is a non-symmetrical one, then you are likely to get axial alcohol or equatorial alcohol, right. If you use lithium aluminum hydride, these are all given in Carruthers book, master book. So, what is the product? Let us say if you have a tertiary butylated cyclohexanone, means conformation is locked, and you reduce it with lithium aluminum hydride, you are likely to get axial alcohol or equatorial alcohol. Okay. And with lithium aluminum hydride you get equatorial alcohol, that means hydride attacks from the axial side. So, that was actually attributed to the stereoelectronic effect, but when you increase the bulk of the reagent, it gives the otherwise equatorial axial alcohol. Okay. So, that was that is the reason why this reagent was named as L-selectrite, but eventually this was found to be selective in many cases. For example, if you reduce alpha beta unsaturated ketone with L-selectrite, you will get only single reduction of the carbon carbon double bond takes place, that means just like lithium and liquid ammonia. That means there are some selectivities obtained from this reagent, and so in organic synthesis it is quite useful, but in this case what you see here, it is little different though. It has a remarkable effect on this oxygen coordination, that means lithium undergoes coordination with oxygen, and the silicons also triggers the fragmentation reactions. So, what happens on this treatment of this reagent, this oxygen of furan undergoes coordination. So, you have this basic skeleton whatever it is, then you have this nitrogen, and this is this bridge 1 methyl group, these things, and this left hand portion remains as it is, oxygen, and then lithium gets coordinated here, and you have the trimethyl silyl group. Okay. So, what do you expect? So, fragmentation means actually today also will give you quite a few example where the furan gets cleaved. So, in this case it is cleaved, that means if this is cleaved, so you will get a carbocation here, that carbocation is compensated by this double bond here, then as usual double bond. So, that means eventually you generate a positive charge here. So, you have a positive charge. So, what you likely to see, 1 to 6, that is it. So, that is it, and this in aryl group, this aryl group will be shifting to this one, shift aryl group, right. So, hopefully I am right. Let us see. Actually I lost the answer, rather I left the answer at home. Okay. So, we will see that. So, how do you see? Basically you keep as it is, and then that means this bond moves here, you have a positive charge, now oxygen, and this is now lithium here, silicon remains as it is, and then the double bond moves, and the double bond moves here, the methoxy, and you have a nitrogen, and then this the bridge carbons, then here. Is it all right? Looks okay. At least electron bookkeeping wise looks is okay. Then you have a methyl group here. What next? What next is, so then you have to compensate this positive charge, I mean neutralize the positive charge, and that is done by the lone pair of this. This is the lone pair effect. So, if this, and then this bond undergoes cleavage. So, that means this one becomes, so the way it is written, you can just write without disturbing anything. Let us say we will have this, we will have this is now double bond, this is double bond, methoxy here, and this is silicon. Then you have the double bond and this O lithium, OMe, all these things, and what else? Then this bridge here, and you have now nitrogen and methyl. So, this is a bridge, and then you have this now iminium ion, right. And the next thing that would be that hydride, that means hydride would be attacking, hydride from this L selectrite would be attacking. So, eventually what you will get is you will get a tricyclic compound. So, tricyclic compound, and if you rewrite, so it would look like this is this, then you have 3 carbon, 1 2, then one more on the side, then NMe. So, you will have a macrocyclic compound, and this is TMS and this is OMe, just this other bond is rotated now. So, what is the lesson we get? See, lesson there are 2 lessons here. One is that lithiation can take place in the saturated furan site, provided all other driving forces existing. Secondly, the lithium also plays an important role in the ring fission or ring cleavage or fragmentation. We will have more example today, but before that just we will look at some of the pyrrole derivatives, some of the thiophene derivatives, okay, and some of the derivatives containing both of these furan, thiophene, etc., then some imidazoles, maybe some oxazoles. We will have plenty of things. Actually, this lithiation chemistry in heterocyclic is very useful, and some of you I guess know, you studied before. There is a famous reagent called tosmic. How many of you know? Raise a hand. Tosmic. Okay, if you do not know, ask Ketoki. She has to write the review on tosmic. Okay, tosmic you must know. Then without tosmic, heterocyclic chemistry is it is due to a scientist from Netherlands, Van Leeuwen. It is sometimes it is known as Van Leeuwen chemistry, Van Leeuwen reagent, but it is a very useful and versatile NCN bond, NCN synthon I should say, sorry, CNC synthon. CNC means carbon, nitrogen, carbon. Whenever you require a nitrogen, carbon, nitrogen, so you can first think of Van Leeuwen reagent or tosmic. We will come to that. I mean, there are so many things actually we will talk about today. For example, you have acetone. I'll just quick before we will come back to this problem. How to do this in one step? One step, I said. Then you have to study all these things. Again, Van Leeuwen. Is that so? Okay. So, in any case, we will come back to that, but just quickly review the pyrrole cases. This is also pretty useful. Pyrrole cases. If you begin with let us say N butyl lithium, so what is expected? By now all of us know. What is our expectation? Lithiation. Lithiation is actually is driven by 2 important factors. You have to keep it in mind. 2 or 3. If you recall, I mean actually 3 different factors. The first thing you should think about the halogen exchange. If you have a halogen compound, I mean there is a likelihood that halogen exchange will be the pretty first, unless the corresponding CH hydrogens are acidic. Next important guideline is the CH acidity, and third is chelation, and of course, combination of all of these things are also there. But primarily in most cases in heterocyclic chemistry, it is, and especially for the 5-membered ring, it is the acidity that drives this lithiation, and that too again if it is next to the heteroatom. For example, I think I told you before, this is a nice way of looking at. This is one of the very useful and reaction. You begin with a vinyl ether. Now, you have a CH3 up here though, then you use tertiary butyl lithium. So many things can happen, right? All these things, all these hydrogens are functionalizable. This hydrogen also next to oxygen heteroatom. This hydrogen is also next to heteroatom. and then all of us know this butyl lithium is minus and this plus. So, it can also undergo Michael addition, all kinds of possibilities are there, all kinds of possibilities, but of all possible reactions, the reaction that you are likely to get actually is this at low temperature. It is a nice reaction though, nice reaction. Okay. And so, that means once again it is due to the acidity of the first of all it was sp2, and then second of all secondly it is next to the oxygen. So, likewise that means in this case in the pyrrole case what you will see, pyrrole case you will see a nice lithiation done, What next? I mean then you can do all kinds of carbon ion chemistry out of the lithiation, and the one of the important reactions in pyrrole chemistry is incorporation of an ester group. You may ask why suddenly ester group? There are reasons also. There is the reason being this most of the pyrrole natural products would contain an electron withdrawing group either at 2 position or at 5 position or in both. Okay. Most of the natural products, because the pyrrole itself is pretty reactive, all of us know. It can undergo polymerization, oxidations, all kinds of things take place. And so, what is then a reagent? The reagent is missing. So, that means especially the research scholars, when you are in the research lab, you must be aware of the commercially available, readily available reagents. What is that? Cyanogen bromide. Then no, I have said directly, one step. Me2 CO3, it does not work, it is pretty inert. No, that is what he said, but it does not work, it is pretty insensitive. And then there is a likelihood also it can actually produce diaryl compounds, diaryl carbonyl compounds like imidazole carbonyl, this imidazole carbonyl. Okay. People and the first try this one, methyl chloroformate. It's a pretty useful reagent though, but there is actually I am coming to another reagent which is very useful, which is this one. Instead of the chlorine you have the cyano, that means or methyl cyanoformate. Okay. This is a very useful reagent. Oh sorry, yes, very good. Okay, OMe. Okay, and this is known as Mander's reagent. I mean there are quite a few advantages. Advantages. For example, if you use methyl chloroformate, the reaction yield is low. If you have a nucleophile which is ambivalent, means sorry, I mean what is that? Ambident nucleophile, not ambivalent, ambident nucleophile, then it can attack at carbon and oxygen. So, methyl chloroformate being hard, so many times it undergoes it leads to O acylation kind of reactions, O carboxylations, and in that context this Mander's reagent is very useful, it gives very good yield. But then there is a problem. What is the problem here? This removal of this methyl group. If you want to have an NH in this position, you have to remove the methyl group here, and then deprotection of methyl group from pyrrole is a tough job, whatever you try to do. So, obviously all of us know what is the next option. If you want to do a lithiation at the 2 position, the protecting group has to be substituted, right. So, what can you do? As usual, not mom, we do in our lab, what is this? Bock. So, you use a Bock here. Bock will give lot of advantage though. Bock will have an advantage, but in it can, because it can undergo chelation with the lithium. For chelation, minimum requirement that it should form a 5 member, at best 6 member, not 4 member. I mean 4 member occasionally suggested, I do not know whether how good it is, but normally if you have a 5 or 6, then chelation is very likely. And but at the same time, then you have to change the reagent, because n-butyl lithium is nucleophilic. So, you have to change the reagent. So, that means you have to have a base, strong base, but non-nucleophilic. Which one? LDA. LDA is non-nucleophilic. Then you have to little more, one more. Okay, good. One more. Tertiary butyl is very nucleophilic, most nucleophilic, most basic of all. You can say, okay, I will agree, fine. Tertiary butyl lithium not basic, but not that nucleophilic. Okay. The other one of the safest one is tetramethyl lithium tetramethyl piperidite. Lithium tetramethyl piperidite. Sometimes we call LITMP. Sometimes simply said LTMP. Okay. So, and obviously, then you have the T-Bock and you get the lithiation done. Then what you can see here 1, 2, 3, 4, 5. So, oxygen can nicely coordinate with the lithium. So, lithiation is favored. Now, the group can be easily protected by all of us know by HF or HBr, all these things. T-Bock is okay. There are now let us look at one more example from the pyrrole chemistry. Let us say you have a situation where you have now we have a polysubstituted pyrrole, and I use 2 equivalents of, let us say, butyl lithium, 2 equivalents of butyl lithium. When I say butyl lithium means a normal butyl lithium, okay. Number 1, and number 2 I use DMF. So, again if you just think about the structure and the possible reactions, you will see there are so many possibilities. The lithiation can take place here at the 5 position. What else? No other position. And normally you do not see the I mean very rarely you see lithiation taking place all other position other than okay, and I mean direct lithiation by deprotonation. So, this is one of these possible site. What else? This you have a possible site here and you have a possible site here. Okay. But when the lithiation takes place here, we call them these lithiation lateral lithiation. We call lateral lithiations. Often we do at in our lab lateral lithiation means side reaction, side chain lithiation takes place. And in this case, the lithiation takes place here at the side chain instead of the nucleus. So, you will get this lithiation done here, then lithiation, reason being so that means you have 2 equivalents of butyl lithium, the one equivalent will deprotonate this nitrogen NH, other with this CHNH. So, you get a dilithium salt. Now, you can see nicely it can form a chelation. So, again it is a combination of the chelation, acidity, all these things would lead to this side chain lithiation and then from the DMF mean DMF is equivalent to is a sort of a, you can say, formyl cation. That means formulation takes place. So, you will have formulation this CH, and then this is double bond, and here you have this thing Okay. What next? Actually, then if you have sufficient base, it can just undergo cyclization. So, what you will get? You will get nice actually sort of isoquinolone kind of isoquinolone. So, pyridine analog of isoquinolone, can be obtained. So, that means you can things little it's more complicated. Let us look at one more example from a 5-member ring, but this is from indole chemistry. This is another way of all of us know that indole, right, if the is treated with an electrophile, what is the reaction done? 3 position. 3 position it is well known, because this the intermediate structure is stable at the 3 position. So, this is the preferred one, preferred mode. And then how to then do rather how to prepare 2 substituted indole derivatives. 2 substituted indole derivative, there is no direct way of looking at. Well, if 3 position is blocked, obviously then next position is available, that is 2 position. And so, what you have to do? You have to do a protection of NH and do lithiation. How is that? So, one of these ways available is to do a protection. Now, again protection deprotection means it should be disliked by organic chemists, because it unnecessarily reduces the yield and also the number of increases the number of steps. So, so you have to be little careful about choosing the right protecting group. In this case, I mean, what do you suggest? Bock, mom, all these things. Okay. But Kartisky, Alan Kartisky, many of you know, is an octogenarian, right? Those who are okay. And he is above 80. How is that? Okay. So, he just treated the butyl lithium salt and then treated with carbon dioxide. So, lithium salt and the carbon dioxide, what do you get? This nitrogen gets protected, and then that means indole. So, take butyl lithium, carbon dioxide, and what do you get? It is quite obvious, right? I do not have to write, because nitrogen get deprotonated, carbon that undergoes nucleophilic addition to the carboxylic carbon dioxide, you get this one. Then you get a little more powerful lithiating agent. So, what you will see, and without any doubt, right, the lithiation takes place alpha to nitrogen, and obviously this driving force, all of us know. Driving force is the coordination of this oxygen with the lithium, the chelation of this oxygen with the lithium. That means 1, 2, 3, 4, 5. So, 5-membered chelate is formed. Now, you can do all kinds of things. Now, you have 2 nucleophiles, ambident nucleophile. This is a carbon nucleophile here, oxygen nucleophile, and all of us know between the carbon and oxygen, carbon is more nucleophilic. So, whatever the electrophilic reagents are used, and this would give rise to the 2 substituted derivatives. So, suppose you want to put iodine up here, and then what do you do? You want to put iodine here. Iodine itself is not a very reactive one, okay, especially in polar reactions. Possible. N-iodosuccinamide is a possibility. What else? No, phenyl iodine acetate, no, that would not give.
So, some interhalogen salts like
ICL is a possibility. So, could be somewhat better, but the yield wise, I think in the last year class I have told you that bromination etc. is done by dibromo. So, diiodoethane, actually what happens, I think all of us know. So, basically it is a source of this, and once you work it up in acidic medium, and you see here the beauty of this protecting group. If you after the workup, what you will get? After the workup, right, and what is this? It has a strong resemblance with a known acid, carbamic acid. All of us know carbamic acid is very unstable, it loses carbon dioxide. So, that means the carboxylic acid protection is quite useful. And okay, let me see, I have another example. I think I'll skip that again from the indole chemistry, but very quickly just look at a few examples from the thiophene chemistry. So, once again it is a very similar one. The reactions of thiophene are quite similar to the furan and the pyrrole, and so if you use again, but it is for example butyl lithium depending on the equivalence. So, and what do we expect? This lithiation would take place, that is it. Then if you compare, I think if you I gave you the example in the last class, right. If you have furan and thiophene, which one undergoes preferential lithiation? Under reaction condition, it depends on the reaction condition, kinetic conditions and thermodynamic conditions, but under coordinating condition it is the furan. Under acidic conditions, means the basic, strongly basic conditions, it is the thiophene. So, that means thiophene CH is more acidic in towards the organolithium compounds because of vacant d orbitals. Okay. So, this is an example. Actually, some this for example, you do not have to do any stepwise reaction. If you use 2 equivalents of butyl lithium, so you will get 2 of them, and then TMS chloride, chloride. Obviously, I think all of us know by now know. So, you will get incorporation of 2 TMS units in the ring. So, I mean similarly, let us say if you want to make a 2 substituted compounds, for example, the compounds could be a 2 carbon side chain, let us say with NH2 or NH something like this. So, what is the missing reagent? That means 1 equivalent of butyl lithium, you get the monolithiation done, and then you have to look for a right electrophile. So, what could be the electrophile? Good, very good. Actually, aziridine, but aziridine alone, just plain aziridine would not do anything. Even alkylated aziridine would not do anything. The aziridine chemistry requires an activating protecting group, groups. In this case, this tosyl, okay. So, tosyl group, and then it undergoes ring opening. So, okay, if for example, you have an ester here, the aziridine would undergo ring opening reactions. And one more example I will give you. This is something quite interesting though. That means, by changing the reaction condition, you can also change the reaction products. For example, if you have a thiophene carboxylic acid and use excess of LDA. So, what do you expect? The first equivalent would go to deprotonate the carboxylic acid, all of us know. Next one, one, two, three, four, 5 positions. Reason being that LDA is non-coordinating, that is what you have to remember. is very basic. Butyl lithium also is basic, but it is coordinating, means it can undergo coordinations with the heteroatoms. Okay. But LDA would not undergo any coordination, because nitrogen itself, nitrogen is there, it is pretty basic, and in this case you will have lithiation done in this here. But if you use butyl lithium, what do you expect? It is a coordinating. That means yes, it is a 3 position. I mean explanations could be, I do not know how it is. So, maybe you have the lithiation and then this coordinate. I mean okay. That means an LDA would break these coordinations, because nitrogen is there, nitrogen can preferentially undergo coordinations with this thing, that thing. Okay. So, that means this sort of, I should say not coordination, is chelation. Chelation is prevented under the LDA conditions. And last example probably from 5 membered ring, we will have one more example from thiophene, and this is a recent paper, the last year published by a scientist from Georgia Tech, and it is 2011. It is a JAX paper. You will see the paper, I mean almost apparently the discovery is very apparent, means apparently means very simple. Okay. Like say if you have a reaction done on benzothiophene and let us say the chlorobenzene, then lithium TMP, and as usual temperature etc. -2, minus let us say -72 room temperature. Okay. Probably okay, I will give you let us say excess amount of, means more than okay, or maybe 3 equivalents of LiTMP. So, what do you expect?
Benzene.
No, I will not expect not benzene. First thing I will expect deprotonation. First, see, whenever you are doing a lithium chemistry, I have told you in the very beginning of the class that look for any halogen exchange. That does not take place, go for lithiation by deprotonations. Okay. If that is not done, then of course nucleophilic additions etc. all these things. So, the first thing that I would assume that the reaction would form this lithiation, and the site of the lithiation is very simple, easy to predict now, next to the heteroatom. What next? That we can say, because excess of we have. So, we will have, now we can see once again a deprotonation. This one also is driven by the deprotonation and the chlorine expelled. So, benzene formation takes place. What next? All of us know benzene is an electron sink, it can accept electron. So, and the reaction product would be this aromatic ring here, right. So, simple addition takes place, simple addition takes place, and eventually what you will get? You will get on work up, what you will get? You will get this. Fine. Now, you have to justify why this reaction or why this particular paper has been accepted in JAX, not our paper. Means what is the special feature of this reaction? Okay. If you look at this target molecule here, what is it? Is it a biaryl, but unsymmetrical biaryl? For symmetrical biaryls, we know the solutions, Ullmann coupling, their corresponding modification etc. would do, right. But for unsymmetrical biaryls, you have a problem. So, that is the reason, and the problem was solved largely by who? those person last year's Nobel laureates, Suzuki, Negishi, all those people. Okay. But then I mean, if those problems are solved, then why this paper should go to JAX? You have to justify. Or what I am trying to say, JAX means this is all of us know, you all agree that it is a high standard journal, that is perfectly all right. That means the quality of the work also should be at par with the standard. So, what is this quality, extraordinary quality of this reaction?
Without that transition.
Very good, Abhishek, good answer. There is no transition metal. Why transition metal is not welcome? Because expensive. Most, of course, not all. Iron, etc., all these things they are very cheap, but these organoboranes, these things, that thing, they are pretty expensive. Then palladium is quite expensive. So, it is transition metal free. That was the title of the paper actually. Transition metal free bi-aryl synthesis and the heterocycles. Okay. And I will give you one more example probably. I think that is and that of course, there are many salient features of these reactions. This is one of these, the transition metal free, and I have in the paper actually there are about 30-40 different examples, and each example gives you a particular lesson. For example, the next example would give you a lesson. You have to find out the lesson here. What is the lesson you learn if these two components are reacted under the same conditions and the products that is obtained same conditions and the product that is obtained is this. So, what is the lesson? In most cases, I will tell you the yields are above 70%. In some cases, the yields are close to 90%. Means the reactions are excellent. Number one. Number two, when I said that LiTMP is the base, but there are many examples which could be performed with LDA, that means much cheaper base. Also, there is also one more base that is actually lithium dicyclohexylamide. Okay. So, that means it is a pretty general in terms of the base, the reaction is general. In terms of the substrate on the left hand side, right hand side, they are quite general, but the generality has been illustrated with various examples. One of the examples is this one. Now, you have to identify the specialty of this particular example. Very good. Little more actually meta substituted.
This is single substitution.
What substitution? Senior substitution. No, it is not senior substitution. Okay, senior substitution. Yes, basically it is regio-specific. Means it gives you a single isomer. In BSc you have studied, if you have a benzene, it could add from either sides, but here actually from only one side. Why?
The carbonyl will be stabilized by the
Not really. Actually, there also it is possible. In traditional benzene, let us say what is the base you use? Sodium amide. That is also possible, right? But if you recall, this is a reaction actually that this should have been taught in BSc, but it is not taught though. It's the reaction. What is the reaction? Is a regio-specific lithiation, and this one, and we call ortholithiation. Ortholithiation is a very famous reaction. We told you that the discoverer of the ortholithiation is who? Gilman and Wittig. Actually, this should have been taught. And then if you use electrophile, you will get, I mean, there is no other alternative, and there is, I mean, there is you will get this incorporation of electrophile. You take carbon dioxide, you get the carboxylic acid, you get this DMF, you get the formamide. All these things are possible, and almost always you get just a single product. There is no question of getting meta or para. So, such a beautiful reactions. Not only that, you can accommodate all kinds of electrophiles adjacent to an electron withdrawing groups also. So, this is a very versatile reaction, very useful reaction, but somehow I do not know why the people are not used to teaching this sort of things in undergraduate. Okay. So, what is it again? The driving force. There are two driving force, two. Because of the inductivity of oxygen, this the adjacent hydrogen is, I should say field effect, better I should write, I should say field effect. This hydrogen becomes more acidic, number one, not the resonance effect. And then of course, this chelation. So, because of the chelation, that means the lithiation, both chelation and acidity, the lithium at the ortho position is very stable. That means, whenever you have a benzene, for example, benzene, and you have something some RLi should add. So, it can add on this side or on this side. So, there are two possible orientations, one the lithium on this side and or of course, and the meta position, and this is R and this is R. And now we know the ortholithiations. That means, the lithiation at the adjacent to an oxygen is stabilized. So, this one would be stabilized, and then that explains the regiochemistry. That explains the regiochemistry. Okay. And then I will give you one more example from this direct arrilation without transition metal. Let us take a case of imidazole, for example. Imidazole, the first condition is chlorobenzene LDA, this is two step reactions. Second is 2 chloro anisole and lithium TMP. So, what do you expect? There are two, actually there are two reactions, two very similar reactions. In one, for the first case LDA, second case is I mean sometimes the choice of bases is done on the basis of the experience, trial and error, etc. Okay. Now, so what is the product do you expect? That means, from the first one you get the phenyl incorporation, in the second one you get the anisole incorporation, but the only thing that you have to make the judgment which one will be placed at which place, that is it. That means, the basic skeletons remains as it is, right. And in all these examples we see that the arrilation takes place at the nucleus. So, now okay, I will tell you the first one would be this one, obvious now is obvious, that is the clue, because it is flanked by two heteroatoms. So, now so what should be the then group? It is the phenyl group. So, if that is so, and then on the other side you will have the anisole, that is it. So, the anisole, then where do I place the methoxy? Where do I put the methoxy group? Meta position, because lithium would be here and the methoxy. So, that means regiochemistry wise, orientation wise, this is a very good reaction actually, and he has done plenty of reactions. Okay. So, it is an imidazole case. Now, let us look at oxazole case. oxazole case. What do you expect? Lithiation, fine. I will where at which now we know the nomenclature. 2 position, fine, and 2 position, right. What next? Okay. I can tell you the reaction, whatever the reaction product was, could not be isolated. That means it was pretty reactive. So, it was trapped with methyl chloroformate. So, what do we expect? So, here something happened. Deprotonation very good, no problem, lithiation took place. So, after lithiation, what is the fate? Normally you have to think about whether it is a kinetically controlled or thermodynamically controlled. If the reaction is allowed and as I am saying that the reaction is prolonged, that means it should give thermodynamic product. So, that means it should give a thermodynamic product. Thermodynamic product could be due to the exchange of the lithiation, okay. And or else a more stable product. In this case, you get a very unique reaction actually. What unique reaction? Again, it is a lithium controlled. In the very first minute, what I said is lithium can cause, if you recall, of all metals, lithium is a nice small metal. It is soluble in organic solvents, it coordinations. Okay, that is important. So, that means that oxygen lithium coordination is a very powerful bondage. Okay. So, what do you expect then? That means lithium should transfer to oxygen, and that is possible. That means it undergoes ring cleavage. So, ring cleavage and eventually. So, what you will find this that means this is what this plus this is minus and now lithium, right. So, and obviously, so what you get is then what is it? Just an isocyanate, and now that means in a nutshell, that means a situation arises when the lithiation takes place in the isoxazole, and isoxazoles have a tendency to undergo ring opening. That is what you have to keep it in mind. The previous case was imidazole. Imidazole dianions are pretty stable. I mean, you can stepwise could lithiate and do this thing, and then the final product would be this is I think we will talk about the cosmic chemistry tomorrow maybe. Well, I will give you one more important kind of reaction. So, these ring openings, okay, and let me give you one more example. Like in this case, it is not a it is not an imidazole, but it is a furan. Then is amine and is amide carbonyl, and this amide carbonyl is linked to a pyrrole moiety and it is a benzyl. Now, you have a furan nucleus, you have a pyrrole nucleus, you have learned all these lithiations etc. Okay, previous one was the imidazole, sorry oxazole, next previous to the previous one was imidazole. Okay. Now we will have a reaction quite just reactions LDA and then this. So, what do you expect? Okay, well, to be since you have already one NH here, so active hydrogen. So, you require 2 more equivalent of bases, it is 2 equivalent of bases. What do you expect? So, first equivalent would give rise to a formation of minus here, then this pyrrole unit, fine, or all of us know they should undergo resonance stabilization, and eventually it would give lithium there. Then you have benzyl. Now, second equivalent, what will happen with the second equivalent? See, so many ES, furan, this hydrogen, pyrrole. So, what else? If you go back, there was a case, pyrrole case. We had an N methyl, we had a side chain methyl, we had this thing, that thing. So, so it is the lateral lithiation. Lateral lithiation, that means the lithiation takes place here at this position. What is the driving force? Chelation. In previous case also, that means you have to always keep track of whether any group is present in the molecule for which is suitable for chelation, and this chelation takes place with this oxygen. Here is nitrogen, nitrogen. That is it. But then if you acidify, you get the starting material back, because protonate here, you get the starting material back. Then it does not give you new product. Actually, or then once you have this, nothing else is possible, then you think of again a fragmentation reactions and affinity towards oxygen. So, it will undergo cleavage, and if you go on, basically eventually what you will get? You will get So, what is the conclusion? Conclusion is that furan can give acyclic structure with 4 carbon, 1, 2, 3, 4. This was originally there, originally was there 1, 2, 3, 4, and that benzylic carbon and then nitrogen. So, you can get this. Okay. So, if that is so, then I mean actually this sort of reactions had some precedence. For example, I think maybe you can go to the literature. I think I maybe yes, okay, this yes, there is a word called zinc. Zinc actually the name of a scientist actually, zinc salts. What is it? Okay, fine. Okay, maybe we'll talk about this thing maybe in the next class. We start from zinc salt and this thing. Actually, we will continue with this topic, for quite some time, another 1 or 2 weeks. This is the lithiation, and then we will talk about the magnesiations. Magnesiation means it's a new word. Actually, all of us know organomagnesium compounds. So, if you have a CH hydrogen, if you put magnesium in the place of hydrogen, it is known as like lithiation, we call magnesiation. So, and these days actually magnesiation is pretty useful reaction.